So in class we talked about separation of variables in the context of diffusion partial differential equation problems. We talked about homogeneous boundary conditions as well as non-homogeneous boundary value problems. And we also talked about how to incorporate the initial condition functions to calculate coefficients in our final Fourier series. Now I'd like to discuss a scenario and what arises when we have a piecewise initial condition function for u of x comma t. And the problem is as follows. So our differential equation is alpha uxx equals u of t, right? A familiar problem. We're looking on the boundaries of 0 and L, so our boundary will be, we'll say ux of 0 comma t equals 0, which also equals u of L comma t. And finally, here's where our initial condition comes into play. Now let's talk about the piecewise function I mentioned earlier, and it's defined as follows. F of x equals 60 from 0 to L over 2, and 0 from L over 2 to L. Remember our boundaries being 0 and L. And f of x is going to be the expression for u of x comma 0, so at time 0, the initial condition as we specified. And graphically, what does this look like? Well, it's a piecewise function because it's broken up into two components, but on the fx plane, xy plane, whatever you choose to call it, we're starting at 60 here on the y-axis, L over 2. So we have that component, and then we have that component. That's the way we're going to define our initial condition. So initial conditions aside, now we can begin our traditional separation of variables problem, where we write u of x comma t is equal to x, big X of little x, t of little t. This is something we've done before. Plug it into the differential equation, so we have alpha squared x double prime t equals, because x is the function of x, and on the right hand side we have x t prime. Now we're going to divide by xt on both sides. Okay, so that gives us alpha squared x double prime over x equals t prime over t. These are two different expressions in terms of they're distinct variables, so we can set it equal to a constant minus k squared, and we'll go from there. Here we're going to move around the alpha, so we have it all in terms of the t differential, which will make sense in a second. Okay, so we have that expression. Now, if we want to rewrite this in terms of the two differential equations, we have x double prime plus k squared x equals 0, and we have t prime plus alpha squared k squared t equals 0. This gives us two expressions for x and t in the k not equal to 0 case. So in this case we have x is equal to a cosine kt plus b sine kt, and t is equal to t0 e to the minus k squared alpha squared t. And this is k not equal to 0 case. For the k equals 0 case, however, we are looking at x double prime is equal to 0, so that means x is equal to, we can call it d plus ex, and t, the t expression is now t prime equals 0, and that's just a constant, so we can just call it c. So t equals c. And those are two scenarios for k not equal to 0 and k equals 0. So now that we have equations for x and t and times when k equals 0 and k not equal to 0, the way we get an expression for u is we multiply the x and the t, corresponding t for each of these k cases. So that gives us an expression of u as u of x comma t is equal to e to the minus k squared alpha squared t, parentheses, a cos kx plus b sine kx. Remember, this is coming from the k not equal to 0 case, and then for the k which we add to it, the k equals 0 case, essentially the steady state one, c plus dx. Okay, and now we're going to try to figure out which of these constants we can do away with. And the way we do that is by applying our boundary conditions. So the first boundary condition was u of x of 0 at time for x0 time whatever is equal to 0. So first let's find u of x, and that gives us well, d plus parentheses minus k a sine k x plus kb cosine kx. That expression times minus k e to the minus k squared alpha squared t. And if we're looking at ux of 0 comma t, which we know is equal to 0, that means that that's going to give us d plus kb, because the cosine expression's equal to 1, kb e to the minus k squared alpha squared t. And the conclusion from that is that since that is equal to 0, that means that d is equal to 0 and b is also equal to 0. And the reason being that this has to hold true for all t values, so d being the constant here, d should be equal to 0. And correspondingly, e to the minus anything can never equal 0, so b also has to be equal to 0. So that gets rid of two coefficients. Now I'm realizing I made a mistake in the second boundary condition, which is actually that u of L comma t is equal to 100, not to 0. And that makes it an inhomogeneous problem, but still possible to solve. Now here we're going to say the new expression for u of x of t, having removed d and b, should just be, remember, c plus a cos kx e to the minus k squared alpha squared t. And from that we're going to evaluate at L for x and set it equal to 100. So 100 equals c plus a cos kl e to the minus k squared alpha squared t. Using similar logic here, we know that if this is going to hold true for all time values, we have two conclusions. One, c is going to equal 100. This holds true for all time values, and a cos kl is going to equal 0, because the e expression cannot equal 0. And so what does that mean? So for the cos kl expression to equal 0, that means that cosine is evaluating at 0, which happens at odd multiples of, so pi over 2, 3 pi over 2, so basically kl is equal to pi n plus 1/2, right? So k is equal to pi over L n plus 1/2. So now that we have an expression for k, we should recreate our formula for u of x of t, right? And it's as follows, which is 100, which is the value found for the constant, plus the summation of jn, which is a new constant that varies with n, cosine pi n plus 1/2 over L, and that whole thing times e to the minus alpha squared t times pi over L n plus 1/2, that part squared. That's minus pi squared t k squared. It's a little messy. Okay, so now we're going to use the final initial condition, which is u of x comma 0 is equal to f of x, which is that piecewise function, remember, and that's going to be equal to, if we plug in 0 for t, we're getting 100 times the summation of jn cos pi over ln plus 1/2. Basically, we're getting rid of the exponential here. And so now we want to solve for jn's, which we're going to use orthogonality to do, but first we need to say f of x minus 100 is equal to the summations of jn cos pi over l n plus 1/2. Now if we use the definition of the inner product, we know that jn should equal the inner product of f of x minus 100 with the base cos pi n plus 1/2 over l, and that whole thing divided by the inner product of the cos with the cos. However, we can do some simplification here. As it shows, as it is, the base, the bottom denominator turns into 2 over l, and we're multiplying that by the integral of the top, which is from 0 to l, f of x minus 100 times the cosine, which this is the base part, times the cosine pi n plus 1/2 over l dx. And this becomes interesting because f of x is piecewise. Remember, from 0 to l, from x goes from 0 to l over 2, we're looking at f of x equals 60, and from l over 2 to l, f of x equals 0. So that's going to be interesting. Also, one final point is that the weighting function we know is 1 here because our differential equation for x previously was in Sturm-Liouville form, so we don't need to solve for a weighting function. Okay, for the final step here, now we're going to actually evaluate the integral. So we have j of n is equal to 2 over l from 0 to l, and rather what we should do is break it up into l over 2, the second to 2 piecewise parts. So let's make that 0 to l over 2, and we know that from that first interval it's 60, and we're evaluating f of x minus 100, so let's say that's minus 40, because 60 minus 100, times 40 cosine pi n plus 1/2 over l dx, and we're going to add to that the integral from l/2 to l, and remember on that interval f of x is 0, so we're looking at minus 100 cosine of pi n plus 1/2 over l. And as it is, if you do the math out, it's a pretty simple integral, and that simplifies to 80 over n pi 3 sine n pi over 4 plus, minus 5 sine n pi over 2. And this is basically your expression for Jn. And what we've shown is that even with a piecewise initial condition, it's not too tricky to do that orthogonality and find the Fourier coefficient in these separation of variable problems, even with the inhomogeneous boundary conditions.